The majority's overall conviction is that the hypothesis of specialists explains how things came to be, which remains the major explanation for the early seasons of the universe. This theory encompasses the advancement of stars, planets, and, ultimately, life on those planets, including ourselves. Despite its odd name, the enormous explosion provides an insightful assessment of what might have happened at the very beginning. The universe was once densely packed into a small area, filled with particles, making it thicker than a pinhead. From this moment, a massive impact of matter and energy occurred, known as the enormous detonation. This event, happening billions of years ago, initiated the expansion of the cosmos. However, historical data has presented anomalies that challenge the assumptions of this theory. When NASA released the James Webb Space Telescope, the largest and most advanced telescope in history, researchers hoped it would substantiate the prevailing speculation about the universe's origins. Tragically, after just 1 year in space, the telescope became immobile. Despite this setback, the James Webb Telescope's incredible capabilities have uncovered countless galaxies, dating back to such an ancient time that it challenges our ability to interpret the origins of the universe. This discovery has sparked serious reassessments regarding what existed before the Big Bang. A pivotal moment in this mission occurred when cosmologist Rohan Natu, using data from the telescope, unexpectedly discovered a galaxy that formed just a few days after the Big Bang, making it the most distant galaxy ever observed. Natu's revelation sent shockwaves through the scientific community, highlighting the astonishing abilities of the James Webb Telescope and its immense potential to reshape our understanding of the universe. This is just the beginning. The telescope promises to uncover astounding insights into the earliest periods of the universe's existence, a time previously difficult to study. Understanding this period holds the key to deciphering the formation of the first stars and galaxies. However, the telescope's discoveries have conflicted with leading theories, revealing galaxies with characteristics that surpass prior assumptions. The unexpected surge of early galaxies has ignited a wave of scientific inquiry, pushing experts to adapt their theories to these new findings. As researchers analyze these anomalies, they face fundamental questions about the nature of the universe and the forces that shaped its development. The James Webb Telescope, positioned 1.5 million kilometers from Earth, is protected from interference and cooled to near absolute zero by its massive sun shield. It combines an enormous primary mirror with incredibly sensitive instruments designed to uncover information about the early universe, data that was previously inaccessible. This period, known as the Cosmic Dawn, occurred around 200 to 300 million years after the Big Bang, marking the formation of the first stars and galaxies. How exactly this process unfolded remains a subject of intense study. Theories range from the influence of dark energy and dark matter to the interactions between gas and dust in star formation. The telescope's unprecedented view of galaxies from the cosmic dawn offers cosmologists a unique opportunity to test their understanding of these complex elements. By studying these ancient systems, experts can either validate their existing models or identify knowledge gaps that could lead to groundbreaking discoveries. Initially, the telescope was expected to observe only a few small and faint galaxies in its pilot studies. However, reality has far exceeded these expectations. Its early images of the distant universe revealed a wealth of galaxies with unexpected ages, sizes, and brightness levels, defying all previous predictions. This remarkable flood of early galaxies has set off a race among astronomers to establish new benchmarks for the earliest known massive systems. With new discoveries emerging continuously, traditional theories are being challenged. Following the revelations from the James Webb Telescope, both experts and observers have rushed to study the existence of these remarkably advanced early galaxies. Some believe that errors in the telescope's data interpretation could explain these surprising discoveries. However, the prevailing consensus is that these findings represent a paradigm shift in our understanding of the early universe. They offer an exciting glimpse into the possibility of a far more intricate and dynamic cosmic history than previously thought. The latest revelations from the James Webb Space Telescope have raised profound questions about the fundamental nature of the universe, challenging established cosmological models. While some scientists seek to reconcile these insights with existing theories, others suggest that these discoveries may be the first signs that the universe is far more complex and mysterious than we ever imagined. As researchers delve deeper into these findings, the implications grow even more profound. If the James Webb Space Telescope's observations hold true, they could fundamentally alter our understanding of cosmic evolution. The existence of such massive and mature galaxies so soon after the Big Bang challenges long-standing models of how the early universe developed. One of the most significant questions arising from these discoveries is, How could galaxies of such size and complexity have formed so rapidly? Current theories suggest that galaxy formation is a gradual process, requiring hundreds of millions of years for gas clouds to condense into stars, assemble into galaxies, and undergo subsequent mergers. However, the telescope's data suggests that some galaxies emerged almost fully formed in an alarmingly short time span, far faster than predicted. This revelation has led scientists to explore alternative explanations. Some propose that the early universe may have contained mechanisms of star and galaxy formation that are not yet fully understood. Others speculate that the fundamental properties of dark matter and dark energy, the invisible forces thought to govern the universe's expansion, may need to be reconsidered. If these forces behave differently than currently believed, they could have accelerated the formation of the earliest structures in ways yet to be explained. Another possibility is that the telescope is detecting something entirely unexpected, perhaps remnants of an even earlier cosmic event predating the Big Bang itself. While this idea remains highly speculative, some physicists have suggested that our universe may be part of a larger multiverse or the result of a previous cosmic cycle. If true, the James Webb Space Telescope's findings could be providing the first observational clues hinting at a reality beyond our current cosmological framework. Despite these exciting possibilities, the scientific community remains cautious. Extraordinary claims require extraordinary evidence, and researchers are meticulously verifying the telescope's findings. Data calibration, cross-analysis with other telescopes, and refined modeling techniques are all being employed to ensure that what the James Webb Telescope is revealing is accurate and not the result of observational errors. Nonetheless, the telescope's early success has already demonstrated that the universe is far richer and more complex than previously thought. As it continues to operate, new discoveries are expected to reshape our understanding of cosmic history, pushing the boundaries of what we know about the formation and evolution of the universe. Looking ahead, astronomers plan to use the James Webb Telescope to study the atmospheres of exoplanets, search for potential signs of life, and further investigate the mysterious nature of dark matter and dark energy. Each new observation brings us closer to answering some of the most fundamental questions in physics. How did the universe begin? What are its ultimate limits? And could we one day find evidence of life beyond Earth? With every image it captures and every dataset it transmits, the James Webb Space Telescope is not just revealing the distant past, it is shaping the future of cosmology itself. Previously envisioned, the most important question at play is our basic understanding of how the universe we know today was created. Primordial chaos and the early discoveries of the JWST could alter our fundamental ideas about cosmic history, revealing insights not only into distant galaxies and structures from antiquity but also into the very nature of our own Milky Way. As Mark Makorian, senior scientist for science and research at the European Space Agency, puts it, "You don't make these machines to confirm theories but to break them. You just have no idea how it will break." The beginnings of the JWST can be traced back to the Institute for Space Telescope Science, STSCI, in 1985, even before the Hubble Space Telescope was launched. Garth Illingworth, then head of STSCI, was tasked with envisioning what might come after Hubble. Despite initial doubts, Illingworth and a small team began laying the groundwork for what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily captures visible light, the JWST was made to observe in the infrared spectrum, allowing it to peer much further into the universe. This capability is critical for studying distant galaxies whose light has been stretched into the infrared due to the expansion of the universe, rendering them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST became the primary instrument for uncovering the mysteries of cosmic dawn. The need for such a telescope was highlighted in 1995 when the Hubble Deep Field observations revealed numerous galaxies in what was once thought to be a blank patch of sky. This discovery illustrated the richness of the early universe and stressed the significance of a telescope capable of probing much deeper into the past. After years of development and a cost of around $10 billion, the JWST was finally launched on December 25, 2021. By July 2022, it was ready to begin its most crucial year of scientific observations. Early initiatives, such as the Early Release Science Program and General Observation Programs, were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded them. JWST observations have tested existing models of the early universe, revealing galaxies that challenge conventional cosmological assumptions. These astonishing discoveries emphasize the significance of pushing the boundaries of scientific inquiry and showcase the unprecedented capabilities of cutting-edge technologies like the James Webb Space Telescope. As scientists continue to analyze JWST data, they may uncover further insights that challenge and expand our understanding of the universe. When the first data began coming in from the JWST, cosmologists eagerly anticipated the results. Many had been preparing their data analysis pipelines for this moment for years. Rather than following the traditional peer review process, which typically takes months, researchers decided to share their discoveries on preprint servers like R14, a platform for research papers that have not yet been peer-reviewed. This approach allowed a new kind of peer review to take place through online platforms like Twitter, where established experts could immediately discuss findings. Rohan Naidu described this process as science by press release, and the ensuing storm of discussion was both intense and surprising. However, there were concerns about the potential drawbacks of this rapid spread of results. Klaus Pontoppidan, a JWST project researcher at STSCI, warned that while the quick sharing of results facilitated rapid dissemination and discussion, it also carried the risk of overwhelming the scientific process. The rapid release of findings, particularly in such a groundbreaking mission, poses challenges to traditional scientific processes. The general consensus among most specialists is that the Big Bang hypothesis remains the primary explanation for the beginning of the universe. This hypothesis encompasses the development of stars, planets, and life, including ourselves. Despite its odd name, the Big Bang theory provides a compelling explanation for what could have happened at the universe's inception. The universe was densely packed into a space smaller than a pinhead, filled with densely packed particles. From this moment, a massive explosion of matter and energy occurred, an event known as the Big Bang. This event, happening billions of years ago, set the universe's unfolding history into motion. However, as scientific data progresses, it has raised anomalies that challenge the assumptions of this theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever built, scientists believed its observations would support the hypothesis of the universe's beginning. Yet, after just 1 year in space, the telescope astonished scientists with its ability to peer so deeply into the universe's past. The James Webb Space Telescope's extraordinary capabilities have uncovered galaxies so ancient that they challenge how we interpret the universe's origins. This revelation has sparked intense examination into what might have existed before the Big Bang. As scientists analyze these unexpected discoveries, a growing number of theories are emerging to explain what JWST is revealing. Some researchers propose that the universe might be older than previously estimated, while others suggest that our understanding of cosmic inflation, the rapid expansion of the universe in its earliest moments, may require significant revision. One of the most striking observations made by JWST is the detection of galaxies that appear far too massive and well-formed for their age. According to the standard model of cosmology, galaxies in the early universe should be small, irregular, and slowly merging over billions of years to form the grand spirals and elliptical structures we see today. However, JWST has identified galaxies that seem to contradict this expectation, fully formed, massive structures existing only a few 100 million years after the Big Bang. These findings challenge the widely accepted CDM, lambda cold dark matter, model, which describes how dark matter and dark energy influence the formation of galaxies. If these early galaxies are indeed as large and mature as they seem, it suggests that either galaxy formation happened much faster than current models predict, or there are missing pieces in our understanding of the early universe. Moreover, JWST has provided unprecedented views of exoplanets, offering new insights into their atmospheres and compositions. By analyzing the light that passes through an exoplanet's atmosphere, scientists can determine its chemical makeup, searching for elements like water vapor, carbon dioxide, and methane, potential indicators of habitability or even life. One of JWST's early triumphs was detecting carbon dioxide in the atmosphere of the exoplanet WASP-39b, a gas giant orbiting a star 700 light-years away. This marked the first time carbon dioxide had been definitively identified in an exoplanet's atmosphere, setting the stage for future studies of smaller, rocky planets that could resemble Earth. As the telescope continues its mission, it is expected to refine our understanding of planetary formation, stellar evolution, and the cosmic web, the vast network of galaxies and dark matter that forms the large-scale structure of the universe. Despite its groundbreaking successes, the JWST's discoveries also introduce new challenges. Some of its observations have sparked debates about the nature of dark matter and dark energy, two of the most mysterious components of the cosmos. While the presence of dark matter has long been inferred from the movement of galaxies, JWST's deep-field observations might provide new ways to test its properties or even hint at alternative explanations for gravitational effects previously attributed to dark matter. Likewise, dark energy, the mysterious force driving the accelerated expansion of the universe, remains one of the biggest puzzles in modern physics. If JWST's findings suggest a different rate of cosmic expansion than previously measured, it could imply that dark energy is evolving over time or that an entirely new force of nature is at play. Beyond cosmology, JWST is also offering a glimpse into the life cycles of stars. By peering through dense cosmic dust clouds that obscure visible light telescopes like Hubble, JWST is revealing the birthplaces of stars and planetary systems with incredible detail. These observations could provide crucial insights into how stars and planets form and evolve, shedding light on the processes that ultimately led to the formation of our own solar system. As the telescope embarks on its multi-year mission, the scientific community eagerly anticipates further surprises. The data collected by JWST has the potential to reshape our understanding of fundamental physics, rewriting textbooks on everything from galaxy formation to the conditions necessary for life beyond Earth. While the telescope was designed to answer some of the most profound questions in astronomy, its greatest contribution may be the new mysteries it unveils, forcing scientists to reimagine the origins and evolution of the cosmos itself.